Welcome to the third lecture in this unit called Explain the Gravity of the Situation. And the quote we have says, "You may hate gravity, but gravity doesn't care." So we want to introduce the learning goals, and the learning goals for this is that you should be able to describe the effect that distance has on the gravitational force, that mass has on gravitational force, and you should be able to use this equation, which is known as Newton's law of universal gravitation. We're going to shorten it as N log. So what we already know, weight is another name for gravitational force. That's something that we explored when we talked about the concept of force. We generally described it as Fg. Now we said that there's a gravitational force that pulls all objects towards the Earth, regardless of their size. Everything that's within the Earth's realm is attracted to the center of the Earth. And we said that Fg was the name of the gravitational force, and on Earth it was Fg equals mg. Now, what we learned in the lab is that there is an attraction between any two objects with mass that we can call gravity. So it doesn't have to just be the Earth, but instead there can be an attraction between the Sun and the Earth, or two people in outer space. There's a gravitational attraction between all of these. We also learn that there's a relationship between force and mass and force and distance. As you increase the mass, the gravitational force between two objects increases at the proportional rate. So if you double the force, if you double the mass, you double the force. You can see that with this linear graph right here. The linear graph indicates, okay, well, if 1 was my mass to begin with and I double it, hey, look, my force doubles as well. If 1 was my mass and I triple it, now my force is tripled as well. Now, it's a little bit different whenever we talk about the relationship between distance and force. Distance and force has an inverse relationship. And we know it's an inverse relationship because as you increase the distance, the force actually decreases. Not only does it decrease, but it doesn't decrease proportionally. So in other words, if I double the distance, that does not necessarily mean that I double that I half the force. Instead, it's called an inverse square relationship. Because if you double the distance, the force is multiplied by 1/4. So it's an inverse square relationship. So let's look at a historical perspective. Newton was the first one to come up with the proportionality that you see here. He built on the work of many others, including Galileo, and there are many astronomers that he built upon. But Newton came up with the idea that force is proportional to g m1 m2 over d squared. Now, the trick to Newton's particular version of this equation is that Newton didn't know this. We now know that it's there. But Newton just said, hey, the force is proportional to m1 m2 over d squared, but he hadn't discovered any sort of equality yet. And Newton's famous quote said, "If I have seen further, it's by standing on the shoulders of giants." That's referencing the fact that he built upon the work of Galileo and others. So Newton's genius. Newton's genius was that this law could be universally applied. That doesn't mean just within the realm of Earth, but what he did is said the gravitational force that's pulling an apple down off a tree is the same force that is pulling the moon towards the Earth, or the Earth towards the sun. So the true genius is this is our first universally applicable law. So in other words, you can use this law on Mars, you can use it at the center of the galaxy, you can use it anywhere. And that's the true genius, is taking everyday observations and coming up with a universal law. Okay, so the first thing we do, it says, astrology suggests that the position of the planets relative to Earth at the time of your birth can affect personality. Examine the differences in gravitational force that Mars exerts on Earth as it's at its closest and farthest. So what you're going to do is you're going to look at the idea of force is proportional to m1 m2 over d squared. Now, you're not changing the mass of the Earth or the mass of Mars in any of these situations. But what is changing is the distance relative to one another. So what I'm going to do is I'm going to say this term right here is d. When I use the term d, I'm going to get a force F. But now I'm going to look at the second situation. What can I say that this is? Well, if you were to divide these by another, you'd realize that 400,000 is 8d. Okay, so what I would do is I'd write the expression again. F is proportional to m1 m2 over, and then I have to put parentheses 8d quantity squared. And this right here represents the second value. Now, if m1 m2 over d squared gives me a value of F, m1 m2 over d squared over here will also give me a value of f. The difference is I'm going to have a leftover term. People get really confused here because they forget to account for the fact that 8d is squared. So another way of writing this term, I'm going to move to the top, is f is proportional to m1 m2 over 64 d squared. What I had to do is distribute the square to both of these terms. Now if you were to look at this, I still have the same m1 m2 over d squared that I have here, m1 m2 over d squared. Remember, that was f. So really what we can say is that f over 64 is what I have left over, because this term is f and I still have the 64 there. So what you're trying to say is that when Mars is at its furthest approach, it has 64 times less gravitational force than it does when it's at its closest approach. Or you could say, when it's at its closest approach, the gravitational force is 64 times stronger than it is when it's at its farthest approach. Okay, next it says a comet experiences a force of F when initially at a distance d. As the comet approaches the Sun, part of it evaporates, losing 1/3 of its mass as it reaches 1/4 of the original distance. How does the new gravitational force compare to the original? So once again, we're comparing forces. So the first one I have is F is proportional to m1 m2 over d squared. That sets my value at F. Now what I want to do is I want to look at the new situation. When I look at the new situation, I would say, okay, I have 1/3 the original mass. So I'd write 1/3 m1. That represents the first mass. The second mass is the mass of the Sun. The mass of the Sun is not going to change as a comet gets close to it. So it's just going to be m2. The last thing we need to look at is the distance. It says it reaches 1/4 the original distance. So what that means is we have 1/4 d, and remember the squared goes on the outside. So now when I want to compare these values, what I want to do is I want to take out the m1, the m2, and the d squared. But I need to distribute the square first. So I'm going to go ahead and just kind of mark through this right here. And when I mark through that, it's going to be 1/16 d squared, because the squared is distributed to both terms. When you distribute the square to both terms, you get 1/16 d squared. So now at this point, what you want to do is you want to go ahead and eliminate all of the other variables. So I'm going to eliminate m1, m2, and d squared. Remember, those are all represented by the value of f. So now I know what f is. I can replace it. It's going to be 1/3 divided by 1/16, and then we have f. So now you should know your rules for combining and dividing fractions. Then whenever you're dividing by a fraction, this term can actually go to the very top. And when you do that, you get 16/3 f. If you're not comfortable using the fractions like this, you can enter your calculator and say parentheses 1 divided by 3 divided by parentheses 1 divided by 16, and you'll get the fractional value, or excuse me, you'll get the decimal version of this. The mastery level question says you have a comet, or the mass of the Earth increases every year from falling asteroids, comets, dust, etc. How many years would it take to increase the gravitational force by 10% if Earth has a mass of this and this much debris strikes the Earth every year? So the first thing you need to do is you need to identify, okay, if I were to look at this, if I want to increase the gravitational force by 10%, if I want to increase the gravitational force by 10%, I really need to increase the mass by 10%. So here's the mass of the Earth, and I need to increase that by 10%, which means that I would need 5.98 times 10 to the 23rd amount of debris. That would represent a 10% increase in the mass. So once I've identified how much mass I have, now I have how much debris falls per year. When you take these things and you divide them out, that will actually give you the number of years. If we have a consistent amount of debris fall in about 2.99 times 10 to the 14th years, the Earth will have a 10% increase in gravitational pull. Of course, that is more time than the Sun has, and the Sun will go nova before then, so you don't expect to see this much of a dramatic increase in gravitational force. Even though Newton was the genius who first proposed the relationship between mass, distance, and force, it took the work of Henry Cavendish, who's often left out of the picture, to turn this proportionality into an equality. Now, the formula you may have noticed at the beginning of this unit was F equals, not F is proportional to. The reason for that is there was something missing, and it turns out there was a missing constant that Henry Cavendish used in a pretty brilliant experiment. What he did is he actually measured the gravitational force between two lead spheres, also known as cannonballs, in this really intricately designed experiment. If you see what he did is he actually suspended, you have two cannonballs right here. But what he did is the gravitational force is so weak between the two, he had to devise this massive device that would measure the attraction between these two things as measured by an angle between the two ropes. It was a really intricate design, but what he was able to come up with the fact that there was something missing. You could actually turn Newton's law of universal gravitation into an equality. And that's what we get when we have this equation right here. You have the gravitational force is equal to the introduction of the value g. G is what we call the universal gravitational constant. Okay, the universal gravitational constant is not something that works only on Earth. When you see a small g means 9.8 because it means Earth. Okay, the universal gravitational constant works anywhere. So if you're trying to find the gravitational attraction on Mars, or if you're trying to find the gravitational attraction between two spacecraft, it will work no matter what with the large g. The large g has a value of 6.67 times 10 to the minus 11th. So it is a very, very large value, very, very small value when you compare it to that of Earth. Okay, so let's put this formula to use. It says, what is the gravitational attraction between two ice skaters separated by 5.5 meters? The mass of the man has a mass of 60, the woman has a mass of 45. So we're going to say M1 is 60, just because that's the first one we ran into. It actually makes no difference because you're going to multiply the numbers together. We'll say M2 is 45. We'll say that D is 0.5. And one thing that we always know is the universal gravitational constant is 6.67 times 10 to the minus 11th. We're trying to find the gravitational attraction, or Fg, and now we can use our equation. F equals g m1 m2 over d squared. Or we can plug in 6.67 times 10 to the minus 11th times 45 times 60. I actually reversed those two, but it doesn't matter. Divided by 0.5, and this is where everybody tends to mess up. The 0.5 is a squared term. Okay, if you were to take this and you were to plug it into your calculator, you would end up getting a value of about 7.2 times 10 to the minus 7th newtons. Now, what you should realize by now is that gravity is an exceptionally weak force. We generally think of gravity as being this extremely large force because it's what keeps the planets moving around the sun and such. But the only reason why it does that is because it has so much mass to work with. Generally, gravity is considered to be an exceptionally weak force. So next, it says a 500 kilogram satellite moves past an unknown mass of 100,000 meters from its center. The satellite experiences a force of 2 newtons. What is the mass of the unknown object? So here's my unknown object. Here's my 500 kilogram satellite, and there's a 2 Newton attractive force between them. So now let's take a look at this. We know that we are looking for the mass of the unknown object. I'll say it's the mass 1. We'll say that we know mass 2 is 500. We know the distance between them is 100,000. And we know the g is always 6.67 times 10 to the minus 11th. The difference between this and the previous question is you actually know F also. Fg is 2 newtons. Once again, you're going to use the equation Fg equals g m1 m2 over d squared. At this point, you would plug in your numbers. You would say 6.67 times 10 to the minus 11th times 500 times m1, we'll say, because we don't know what that is, divided by 100,000 squared equals 2. At this point, you would go ahead and rearrange algebraically. You would multiply both sides by 100,000 squared, and then you would divide both sides by this top term, And whenever you do that, you should end up with a very large number for the mass, because you should expect to get a very, very large mass for any sort of gravitational attraction. And when you do this, you end up getting something like 9.97 times 10 to the 17th. Now, determine how far a satellite must be placed from an asteroid to produce a gravitational force of 10 newtons. Whenever you do this, you should realize that you have 5,000 kilograms and 1,000 kilograms, so you have both masses, M1 and M2. So 1,000 and 5,000, and once again, it doesn't really matter which order they're in because you're going to multiply them. Remember that you always know G, and then in this case you also know F as well. F is 10 newtons. The difference is you are trying to solve for the distance. Now the distance in this case, we're going to use Fg equals G m1 m2 over d squared, Newton's law of universal gravitation, and we're going to go ahead and plug in. We're going to say 10 equals 6.67 times 10 to the minus 11th. We're running out of room here, times 1,000 times 5,000, and all of that is going to be divided by d squared. Now what you should realize is you're going to have to actually isolate for d. Remember, d cannot be in the denominator. It's got to be in the numerator. So I'm going to multiply both sides by d squared, and I'm going to get 10d squared equals, and then you can multiply this term out if you would like to. I'm going to go ahead and write it out still, but if you feel more comfortable working with one number, then you can go ahead and write it out. Okay, once you've done this, you will divide both sides by 10, and then here's the thing that everybody forgets. What you have now is d squared. What you need is the distance. So whenever you take these and divide them out, in order to get you have to take the square root at the end. When you do that, the distance ends up being a very small number of 0.0057 meters. And somebody says, well, that's really small, that's like 5 millimeters, and you're right. That's the only way you could produce this large of a gravitational force between two relatively small objects.